Here I'll show you a small example of using compiled blocks in Houdini to make your tools run faster. Compiled blocks are actually not that well known feature, but it's quite awesome and powerful. So first let's start by creating an empty geometry node. And let's have some geometry to work with. We'll generate random points on this geometry. So let's create a first compiled block. So what's special about compiled blocks is that whatever goes on inside this yellow box, Houdini will try to compile all the nodes in a way that they are executed as basically as a one function, one piece of code, and therefore it will happen much faster than executing each node separately. Also, the memory usage will be lower because, like, traditionally each node will have sort of like a separate copy of all the points and vertices. Of course, there's like an optimizations behind the scenes, but theoretically that's the way it is. But in the compiled block, it will be treated as a one node, and therefore there'll be only one copy of the geometry. And because of that, compiled blocks have several limitations. You can read about them more detailed in a documentation. But basically, the couple of main limitations are that the nodes inside the compiled block cannot access anything outside the compiled block. For example, they cannot reference geometry that's generated outside the block, except, of course, what's coming in through the main begin input node. And another limitation is that some nodes are not supported. Basically, Houdini they are trying to convert more and more nodes each version, since version 16 when the compiled blocks were introduced, but still there are several nodes which are not supported, and these are usually older nodes or more complex nodes. But of course the good thing is that as with everything in Houdini, you can do things in several different ways, so usually you can find some other workaround way to do something if a particular node is not supported. There are two ways how you can use the compiled blocks. First one is just connecting it to your network as regular nodes, but that's actually not that useful. Another much more useful way is using the Invoke compiled block node. This way you can call your compiled block without actually connecting to your main network. And the main benefit of it is that you can actually call it several times, like the same functionality in different places without copying nodes. It's actually very similar, like creating a function if you're familiar with programming languages. To use the Invoke node, there are a couple of things you must do. First, you must specify the compiled block you want to call. Usually you pick the end node of the compiled block. And then the second thing is naming of the begin nodes. So your compiled block can actually have several begin nodes. By default, there is just one. You can actually create multiple begin nodes, and to let Houdini know which begin node you want to map to each input of the Invoke node, you must give names to your begin nodes. So each begin node has a name. And then in the Invoke node, you also must write the name corresponding to each input. For example, if I write geo here in the first line, it means that the first input will go to the begin block with the name geo, and the second one will go to the params. Okay, so let's actually create something using compiled blocks. For our example, let's start with generating some random points. So how do we specify the number of points we want to generate if we cannot reference anything outside the compiled block? Well, technically you could reference, like, for example, like a parameter outside the network if you have like a custom parameter on your object node, but that's not like very optimal way, because it will always like have a hard reference to this one parameter, and you would like to design your compiled blocks as functions, so you can pass like your parameters to the different parameters to your compiled block, and every time it will generate some kind of different result. For example, if you call it in different places, you want to pass different parameters. For example, from here you want to generate 10 points, and from here you want to generate 20 points. So a better way is to use different mechanism of passing parameters. And for that we can use another input node. Let's create another block begin node. Let's call it params. So what I like to use is just a attribute wrangle node, and using the detail mode you can set some kind of parameters. For example, count 10. Now this is just an empty node, no geometry, just the one detail attribute named count. You can plug it in as a second parameter, set the name params. So now this will go into this input block named params. If you want to test, like see what each node inside of compiled block does, if you like enable it now, of course it's empty, because it's, when you activate it here, it's not connected to anything, and it doesn't know that this invoke node actually calls it from somewhere else. So for testing purposes, it's always nice to actually plug the inputs in directly, so you can test your compiled block, and then when it's finished you can disconnect it and move it somewhere else. So here you can see that now this begin node actually has this detail attribute we're passing in, and this has the input sphere. So let's change this. Just to make it nicer, let's rename the nodes. So here, let's reference as a detail attribute. Okay, seems to be working, but actually it is not. You see, as soon as I disconnect the inputs from the compiled block, it gives nothing. It's actually, it should give an error, but I don't know, sometimes whenever you're doing something wrong with compiled blocks, Houdini usually shows like an exclamation mark and tells that something's wrong, you're referencing something outside the compiled block or something similar. But in this case it doesn't give any warning, and it might be a bit confusing. But the thing is that actually this is not the way to do things inside compiled blocks. Well, you cannot reference nodes inside compiled blocks using the expression like path in your expressions. What you must do is use spare inputs. So what's spare inputs? If you don't know, you should read it about it in documentation, but actually it's very simple. So you select your node in which you want to reference some other node. You just click the little gear, click add spare input, and then you have like a new parameter where you can reference another node. Let's just drag in this node we want to reference, and then in your expressions you can reference your spare inputs using minus some number. Like first one is -1, you can have several more. Second one will be -2, -3. And that's actually quite a handy way if you don't like to write path in your expressions. You can use it also in other places, not just inside compiled blocks. It's just because it's just easier to write -1, not like full path in your expressions, to also make your expressions shorter and more readable. And also you see here's like this kind of, it's maybe hard to see in the video, there's this like blue line which shows that this node actually references this node, and so you can kind of more easily see your connections between nodes. And this way everything starts working, because when using spare inputs and in compiled blocks, it allows Houdini to know beforehand that okay, this node will use this node, and so through some kind of internal magic during the compilation it can do things correctly, and everything will work. So this is the way I like to use compiled blocks, by having a separate node which is called parameters. I usually give it some kind of different color, shape, just to make it easier to see later when I want to change some parameters. So you see now we have this count parameter, we can change it and compiled block produces different result each time. So let's continue building our little example. Let's connect back the kind of the test values, test inputs, so we can work, like see what each node inside compiled block does. So let's create some polygon lines. Let's just connect all polygons. They'll be in some kind of random order because the point generate will just generates random points on the surface. Now it's actually one primitive. For example, we need each line to be a separate primitive. Let's use a poly cut node and just cut all points and strategy cut. Now we have 19 primitives. There will be some duplicated points, but that's okay. So now let's loop through our lines for each primitive. So let's talk about loops. When you select the end node, you can see there's this checkbox, multi-thread when compiled. By default is disabled, and usually if you use the loop somewhere else, it does nothing. But if you use a loop inside the compiled block, it's actually quite cool. When you enable it, it allows compiling loop in a special way that each kind of everything what happens inside the loop is also sort of like another compiled block. So each iteration can be executed as a separate piece of functionality, and Houdini can actually run each iteration in parallel. So can basically, if you have a multi-core processor, it can run your loops very efficiently and much faster. But when doing so, it also imposes several even stricter limitations on the loop. Similarly, as in compiled block, you cannot access anything. All the nodes inside your loop cannot access anything outside the loop, even the nodes which are inside the parent compiled block. What I mean by that, I'll show you a bit later. So let's just continue with our example. Just enable single pass, just have some piece we can work with. So just start by sampling it. 50 segments will be okay. Next, add a point triangle. Searching for functions for doing cable deformation, I found this kind of nice piece of code for doing so-called catenary deformation. It's basically like a hanging cable, hanging curve type of deformation. I'll just reuse it. I'll not go into the details. It's kind of a bit of a trigonometry problem. But for this formula, you need two parameters. One is the curve u, which actually can be easily generated using the resample node. It's actually just from one parameter from 1 to 0 on the points, which indicate like how far along the curve the point is. Second parameter is the slack value. It's actually a number which tells how much your curve should drop down. It's a float number. It's not kind of a user-friendly value from my experiments. The best range is like from around 0.14, which gives you quite a large drop. I feel that more than this it will not look natural, and around 5 is almost a straight line. Well, 1 is also almost quite straight, but not completely, and so the value change is not a kind of a linear effect, but it's more like a curved. So for us, what we want to have is more user-friendly input. Let's say 0 is like a straight line, and 1 is like this maximum drop. So let's remap the kind of values using the simple ramp. Before we do that, we need to specify some kind of input parameter we want to have. Let's add it through our parameters node. So now we have, sometimes if you don't see like changes, now it is updating, but sometimes it kind of caches the compile block, and so now we have our slack value as an input parameter, and let's try to use it inside our loop. And that's the thing where I mentioned that the for loops inside compile blocks are a bit tricky, because we cannot actually reference the parameter node directly. If we try to, for example, just well, now it works, but as soon as we kind of click at the end or invoke node, it actually shows an error, and that's what I mentioned before. Like basically, it says that you're doing something wrong. You're trying to access something outside the block, the for loop, and that's not allowed. So how do we solve this? We can try using the spare inputs, but that actually will also not work inside the loop. It would work outside the loop inside the block, but not inside the loop, because loops are even more restrictive than the compile blocks themselves. So how do we solve it? Let's remove it. The way I found to solve this is basically the only way you can pass in some input into your loop is through the begin node. Whatever goes in, it's accessible. So let's just use simple attribute copy before the loop and copy all parameters on the main input geometry. Let's remove this. Just let's copy all detail attributes. So now we have copied all the parameters on the main geometry, and inside the loop, well, now it doesn't show this, but it's just because Houdini, probably it's just a bug, but sometimes it caches the input of the for loop, and it will not update it automatically. So you need to click the reset cached pass, and as soon as you do it, you see that all your parameters are now there on the input geometry. So now we can just access them directly from the first input, from the main geometry, because it's there in the details. So as I mentioned, we need to remap our input parameters from a user-friendly range of 0 to 1 to the actually range that's used by this formula. So we can use a ramp for that. So let's remap the input value of 0 to 5, 1 to 0.14, that's 0.5 to approximately 0.3. Let's change it to be more smooth, and just it doesn't have to be precise. Basically, it's just a very non-linear kind of way of. It's just this way I have found it to work best and be more user-friendly. So what's next? Let's see how it all works together. Now we have a bunch of cables hanging down, all similar. We might want to add some kind of randomness to it. So let's do that. Maybe introduce some kind of random slack range we want to use for each segment. So let's remove this and add a different parameter. For example, from 0.1 to 0.9. We have it in our details. Let's update the cache. So first let's read it in. Let's generate a random number. that we need some kind of seed. Let's use loop iteration numbers or seed. Just plug it in as a second input. Because it's inside the for loop, we can use it directly. So iteration detail attribute. So seed and right now each cable has a random slack value. We still want to randomize it now, like each time it's called, we'll use the same seed for the loop. So we want to have some kind of parameter outside the compile block, so we can, for each time we use it, we can specify different kind of master seed. Let's add it as a parameter. And let's update the cache. And let's just add it as one thing I don't like about this visually is that, like, if the points are very close to each other, then this curve slacks too much. It doesn't look that realistic. So we might want to change it. So if points are closer to each other, then we kind of reduce the slack value. It's just the way how this formula works. It's basically when you move points closer together with the same input parameters, the hangy part will just grow taller and taller, and if the points are really close, then it might even like go almost to infinity. So let's first measure the distance between the points. We'll use a primitive wrangle node for that. Have just one primitive in each loop, so we can just both points we want to use. Now we know the length of the distance between points. But because points can actually, they are in 3 dimensions, and they can, well, the length can be quite large, but they can actually be, if looking from the top, they are quite close. So let's account for that and just nullify the y coordinate, so we care only about the horizontal plane. And now let's just divide our slack value by the length. Now it's probably too much. Oh no, sorry, I'm actually dividing by 0 because this is a primitive attribute between points mode, so we actually need to read from the primitive. We have just one primitive, primitive number 0, and we read it from there. And let's just use this variable. So now, actually, for points which are quite far apart, it will increase the slack because the distance is larger than 1. So we don't want that. So let's just clamp it between 0 and 1. We care about only points which are really close together. So now just the points which are closer, they'll never hang so far. We can actually add some kind of user controllable parameter just to tweak how much of this effect we want to have. So we can just tweak it. Okay, and the last part is let's generate some geometry from the curves. Use the sweep circle. Let's change it to polygon. It's a bit too thick. Also, I think the normals are reversed. Let's just reverse them. And let's add the thickness as a parameter, external parameter. And now we can reference the parameters block through the spare parameters because it's already outside the for loop. Let's add spare input. Drag params here. Let's just -1 radius. Alright, now let's test it. Yep, works. So yeah, now basically we have our compiled block finished, and let me show you the power of using invoke nodes. Let's just duplicate it and use the output of first invoke node as an input of the second invoke node to generate cables hanging from the first cables. Let's merge them. And let's change the parameters of the second call to generate the thinner nodes. Let's just duplicate our parameters node and let's have them much thinner. So you see now this is the powerful part of having all the parameters as an input for the compiled block, not like some kind of global parameters referenced through expressions, because you can have different parameters for each call. Basically just one input, one functionality, one compiled block which generates different results based on the input parameters. Let's generate, for example, 100 curves this time, and let's make them really saggy. And let's do it once more. Now we have curves from the curves from the curves, and we can do it as much as we want. We can generate from all of them. Let's just change also our seed and merge these together. You see, now we have some kind of complex setup going on by just reusing the same functionality over and over. And so I think it's just a cool and powerful way to make things in Houdini. We can now cut the inputs, so we can move it just over from our main network, so it doesn't clutter up our node connections. It's just a nice way to work. I like it. And not to mention that it's actually very fast. It's much faster than if you would just do it regularly without the compiled blocks. We can just test it. Let's add some kind of animated deformation. So now every frame it regenerates all these cables, and it's pretty fast. I think the slowest part is actually the sweep node. If we disable it, it's much faster. Oh, we can't do much about the sweep node. That's just how it's built inside Houdini. We cannot kind of influence that. And if we let's disable, let's just compare. Let's just disable the compiled checkbox. It's not that noticeable now because our network is quite simple, but actually the speed up can be quite dramatic. Also, if you're using a lot of loops inside your compiled block, it's even gives more speed. So that's it. I hope this gives you some kind of interesting ideas to explore and better understand the benefits of using compiled blocks, which are awesome, especially if you're making tools for Houdini engine, where speed is quite important. Like when your artist will tweak parameters and want to see the result as quickly as possible, or for example you have some kind of interactive handles you drag around, and it's quite nice for your tools to be responding in real time, not waiting like 2-3 seconds every time you move something for it to update. So good luck, and let me know if you want to know more about this topic.